now we've had 3 leading module makers speak, and so we move ahead to materials and equipment to save on cost. So we first look into metallization, and we're happy to have with us Zinan Zhang, who is the technical director of Solamet, and he will speak about innovative metallization solutions for TOPCon efficiency and cost optimization. Zinan, the floor is yours.
Okay, thank you, Michael. Let me share my screen. Let me see. Can you see my screen?
Yeah.
Okay, let's go. Thank you.
Go
Hello,
to
everyone. Yeah.
You can see still the Microsoft symbols if you click on mode.
Is it okay now?
I think you can still see that. It's okay.
Okay, let me, sorry. Let me check. Sorry. Let me restart the software. Can you see my screen now?
Yep.
Is it okay now?
You can see still the symbols, but it's okay. Let's go.
Okay. Hello, everyone. Thank you for the opportunity to present today. My name is Zinan from Solamet Material Science. And today I will discuss the innovative metallization solutions for n-TOPCon efficiency and cost optimization. And this research explores how advanced metallization technologies can boost the efficiency and reduce the cost of n-TOPCon solar cells. And Solamet is a metallization paste supplier. On July the 1st, 2021, Solamet acquired DuPont's metallization business and significantly enhancing its innovation capabilities and broadening its product portfolio. And Solamet is now a recognized industry leader in metallization with extensive intellectual property. And Solamet has a strong global presence with headquarters in Zhejiang, China, and offices in Shanghai. And our R&D centers are in Shanghai and Taoyuan, Taiwan. And Solamet has a comprehensive portfolio spanning P-type and N-type solar cells. Over the past 2 years, as N-type cells have become mainstream, we have developed the solutions for TOPCon, BC, HAT, and PROSCAT, continuously refining our products to lead in technological innovation. And 2 trends are shown here: the mass production efficiency in China, with HAT and TOPCon leading, and by the end of 2024, the market share of TOPCon technology will exceed that of PERC and reaching around 70%. Okay. And this slide outlines the 4 stages of n-TOPCon technology development in mass production from 2021 to present. And the stage 1, from 2021 to 22. And the TOPCon with a homogeneous P plus emitter using the silver aluminum pastes and achieving mass production efficiency of around the 24.5 to 25%. And the stage 2 from the first to third quarter of 2023, the TOPCon with LDSE still using the silver aluminum pastes, and now combined with the selective emitter technology such as SE. And the last stage saw a slight increase in efficiency, reaching around the 25.2 to 20.3 around. And the stage 3, from the fourth quarter of 23 to the first quarter of 24, and TOPCon with SE and the LECO, and using LECO paste with the mass production efficiency improving to around the 26. And stage 4, from the second quarter of 24 to present the TOPCon with non-SE and the LECO, eliminating the SE technology and reducing the laser induced defects, and the mass production efficiency goes to around the 26.5 or above. Yeah. And looking ahead, the question arises, what's next, and how will n-TOPCon continue to evolve after these technological breakthroughs? And this dive focuses on the key metallization related aspects of n-TOPCon efficiency improvement. The main loss, the main efficiency loss mechanism include the optical losses, surface recombination, and the current transport. And this efficiency losses suggest several potential areas for improvement. And in the middle of this slide, marketing green, and we can see the cell efficiency improvement technologies include the fan-line screen printing, the front-side polyfinger, the boring diffusion with high R sheet, and the passivated edge technology such as PET, and the rail-side poly optimization. However, these technological advancements bring about new metallization challenges. And these challenges include the good printability, and the low line resistance, and the silver silicon contact versus metallization recombination, the balance between them, and good cell thermal stability especially after LECO process. And those connections will be explored in detail in the upcoming slides, starting with the fine line screen and the challenge. And here, this slide and evaluates paste printability using the gradient opening screen to test the paste. The screen was designed with openings that gradually shrink from 14 to 6 micrometers, repeating this design pattern 5 times across the screen. And this allows for a single printing experiment to evaluate the paste printability at different opening size at the same time. And the EL performance and under the grid line resistance, such as RGL, and the microscopic morphology results are highly consistent in characterizing the printability of paste. And you can see in particular the sample 3, the system 3, demonstrated low RGL and a very uniform grid line morphology. And the sample showed the best performance with the lowest RGL at about 8 micron opening, and its morphology was highly uniform in the microscope observation. In contrast, the system 1 and system 2 exhibit higher line resistance and poor morphology at the same opening size. And the system 3 is currently in mass production at customer size with around 8.5 micron opening screens. And this slide continues the discussion on the fine line printing, focusing now on the ultra fine line applications. We used a new set of RGL data with opening ranging from 3 to 11 micrometers and narrowed than those in previous slide. And the results show that the system 456 demonstrated safe printability at 7 micron opening screen. Notably, the system 6 showed a best printed potential on a 5 micron opening screen with the lowest RGL value at this size. And in ultra fine line printing, the influence of the silver particle size on printability becomes more and more significant. The paste is composed of several key ingredients: binders, solvent, thick sorbic agent, and the silver powder and the glass. While organic components play a significant role in printability, the impact of the silver powder becomes even more crucial as we move to the ultra fine line. And this slide focuses on the selection of the silver powder for ultra fine line printing. First, the D100 particle size distribution of silver powder must be strictly monitored to remove the large and irregular shaped particles. And the SEM imaging here show the example of the large particles that need to be eliminated from for the optimal performance. And the second, it is essential to fine-tune and smooth the surface morphology of silver powder to improve both its performance and uniformity. And the images here show the silver powder before and after the polishing process, where the surface is significantly smoothed and enhanced printability. And finally, by optimizing the ratio of different silver particle size, the solid content and viscosity and the sintering density of the silver paste can be balanced. And this improves the fine printability of the paste and helps reduce the grid line resistance. The diagram here illustrates that using a blend of different silver particle size as opposed to a uniform size particles ensures better utilization of the gaps between the large particles, allowing for a more balanced paste with improved flow characteristics. And let's now turn to several efficiency improvement processes related to the balance between the silver and silicon contact and metallization, metal recombination. And those include the front side polyfinger, the boring diffusion with higher sheet, and the rear side poly optimization. And let's start with the rail side polysilicon optimization. Several optimization strategies are being explored for the rail side polysilicon layer. And one approach is the double polysilicon oxide structure, and which showed improved preservation and increased the carrier lifetime and reduced the contact resistivity and boosting overall cell performance. And another strategy is to maintain a thick polysilicon layer in the metallization region while thinning it in the other region. Yeah. And another method, the middle one, the other method involves using the rail-fed polyfinger with a thick aluminum layer, which replaces polysilicon in the non-metallized region and reducing parasitic absorption caused by the polysilicon. And moving to the P emitter diffusion optimization in the middle. And as the front arc sheet of n-TOPCon cells increases, improving the balance between the contact and recombination becomes crucial. As shown in the table, the paste B, here, the paste B showed better balance between the recombination and the contact than paste A, and improving the efficiency on the higher sheet wafers. The data reveals that paste A faces a contact bottleneck at higher sheet with significant fill factor loss. And in contrast, the paste B strengthening the contact performance, yielding higher and overall the efficiency despite in a little bit lower VOC gain compared to the paste A. Yeah. An open question is how much higher can arc sheet increase? And it has already risen from 150 to 400. But what is the upper limited? If the metallization paste reach a contact bottleneck, and will SE technology be reintroduced? So I think this is those are the open questions. Yeah. And let's discuss about the front side poly finger, actually a bifacial TOPCon structure. The introduction of a poly structure on the front side helps address preservation defects. However, questions remain regarding the process of complexity of the front side poly and the potential for the parasitic absorption and whether the large contact points generated during the LECO process could damage the front side poly layer, and will big adjustment to the metallization paste be needed to achieve overall efficiency gains? So I think this is also an open question, and we will see. Maybe the market will tell us the answer. Yeah.
Zinan, 3 minutes.
Okay. And this slide is just talking about the mechanism of the N plus poly, and I think this mechanism is quite similar to the PERC cell. So I won't talk more about the mechanism here, and the key point is to the important factor is the glass and the silver in the paste, and also the results will be influenced by the preservation layer and some other such as the fairing profile and so on. Yeah. And this is about the mechanism of the P plus, and actually there are many literatures talking about the mechanism about the LECO process. So I want to go deep about this part. And what I want to say is also that the key factor is the inorganic part, the silver and the freeze, or we call it the glass, and they co-work with the diffusion technology, with the fairing technology, with the laser optimization. Yeah. And last is about the PET. Actually, the PET can use to reduce the efficiency loss caused by the surface recombination, and however, we should mention that this requires the paste have a good the paste, not the paste, the cells with the LECO paste have a good thermal reliability. So we observe that in the simulation test, we observe that when during the similar process, such as 300 degrees centigrade for 30 minutes, and we found that the degradation of the cell efficiency. And so this is we need to improve the paste and improve the cell to have a better thermal reliability. And the last part is about the reduced silver consumption. And currently, two main approaches are being used by cell maker to reduce silver consumption. One is fine line printing, and another is to use the low silver contact paste on the rail side. And these approaches are have reduced the total weight from maybe 130 milligram to now less than 80 milligram on 182 wafers. And another actually but the 0BB can also use to reduce the silver consumption. And we have successful to lower the solid content from 91 to 89 in mass production. And the one open question is how about the front side paste? And the answer is possible, but it is possible but not priority. And the last part is about some silver-free paste. I think the copper solutions for TOPCon was studied by several research institutes, and but more scale up opportunities maybe in the hybrid BC or AJD BC area, and maybe not in TOPCon now. Okay, and this is my summary. And sorry for the time, I won't read this summary, and that's all for my presentation. Thank you.
Zinan, thanks. That was very detailed. Great, actually. I think there might be some questions because there was so much fodder. Just one question on your last slide. What about actually copper? You said it's rather something for BC or HJT, but there is work, and obviously, as we learned from Alex, silver prices are supposed to go up, and you rather don't want to compromise on efficiency these days. So how are you looking into that, and what would that mean for you if there would be an entry of copper? What would that mean for Solamet?
Yeah, actually, we first the Solamet also do the study and do the development of the copper paste. So actually, several years ago, when we are in DuPont company, we just have the copper project, and so we are not the only the company only sell the silver paste. So I think Solamet is open for that, and for the copper paste they use in TOPCon, I think it is possible, and it is several studies are around the TOPCon copper paste use. However, as you know, there will be new capacities of BC in China tomorrow, not tomorrow, next year, 2025. And they several the cell makers just evaluate the silver free solutions. So as I know, the copper is one option. So maybe, and because the copper solutions also related to the equipment's reliability, and there are many ways and many things to do for copper's the copper's mass production in high temperature application. So I think the BC will accelerate this process, and they will go together to the market. So I don't think from the technical way, the copper used in TOPCon, the answer is yes. And from the market way, I'm not sure which will be first come into our side. I guess it is the copper with BC.
Okay, super. Thanks a lot. I think there are some questions also in the chat. If you could answer them, that would be super nice. Thanks again for this very detailed overview on developments in silver paste.